talking as a way, so I'm introducing the speaker. And it's my pleasure to introduce our seminar speaker today. It's Dr. Elie Bou-Zeid. Is it good enough?
Excellent.
Elie got his PhD from Johns Hopkins University in 2005, and currently he is an assistant professor at the Department of Civil and Environmental Engineering at Princeton University, and he has published quite a few papers over the years. And his interest in environmental fluid mechanics, turbulence, boundary-layer problems, urban climatology and hydrology, surface-atmosphere interactions, buoyancy effects and turbulent flows, and wind energy modeling and forecasting. And let's meet Professor Elie Bou-Zeid.
Thank you very much, Marat. So, as you could suspect from the title, today I'm going to mainly talk about direct and large eddy simulation of stable atmospheric boundary layers. I decided to focus more on the LES part today than the DNS, and mainly how this kind of LES of idealized turbulent flows, how they can help us understand the influence of stable boundary layers on weather and climate models, and how they can help us represent these boundary layers better. Obviously, the bulk of the work was done by not me, but by my postdoc Jing and my PhD student Timon. So a lot of this work is due to their hard work and long hours. So basically, whether you're an earth scientist or an environmental engineer, the aspects that we're interested in, of the geophysical aspects that we are interested in, are quite similar. We're interested in our impact on the planet. So how much, how does CO2 emissions alter the climate, or how does urbanization create a hot local microclimate? And we're also very interested in the reverse part of this equation, which is, we're also interested in the reverse part of this problem, which is how this basically natural systems impact us. So how would climate change basically affect our livelihoods? And if you are interested in this aspect especially, you need to get your basically climate or weather prediction right in the locations where we live. So you need to get it right close to the surface. So you really need to have highly skilled models close to the surface. And the problem is, as you get close to the surface, you basically get a lot of, for example, surface variability and heterogeneity that complicate your picture and makes things very, very spatially heterogeneous compared if you are in the free troposphere. Also, another problem is that, again, especially as you get close to the surface, you have a very large range of scales that you probably cannot cover in a single model, but that are interacting. So how do you deal with this? If you're doing a large-scale coarse modeling, and I lump weather and climate model in the same category here, even though I shouldn't, but these are coarse models. And the reason I lump them is that both of them cannot basically capture any of the fine-scale flow and the other processes happening close to the surface. So with these coarse predictions, you have a lot of unresolved physics close to the surface, and in clouds and other areas. Now, you could, if you are interested in this kind of area close to the surface, you can zoom in. So you're zooming in at what we call the atmospheric boundary layer. I'm sure you all know it. It's the first kilometer of the atmosphere, separated by a capping inversion from the rest of the troposphere, very highly turbulent. And very close to the surface, we have what we call the surface layer, about 100 meters, and here the impact of the surface is very large. So if you are interested in this region where we live, you can zoom in on this and you can even model it. And if you try to model this part only, obviously you can refine or resolve a lot of the processes that climate and weather models cannot resolve, but still you have some subgrid scale processes. Also, the problem is here, you can only do a limited domain. So you have limited spatial and temporal scales that you are resolving, and you don't know the boundary conditions of your domain that are driving it. So you don't know what is the large-scale synoptic patterns or mesoscale dynamics that are driving the flow in the atmospheric boundary layer. So what we often do in this case, and it's a problem I'll come back to later, is we say, okay, well, there's a scale separation, and the large scales are kind of steady, so I have kind of a very steady state, or very kind of, the turbulence is in equilibrium, and I have kind of just a steady state boundary layer flow. The reason, again, we're interested in the boundary layer is that we live there. So if we want to say how will climate change impact agriculture, we really have to know what, how the climate changes, basically what happens in this fine layer. But also globally, because to get the large scale circulation right, or to get the mesoscale dynamics right, you really have to know what's happening in the boundary layer. And the reason being, half of the kinetic energy dissipation in the atmosphere is dissipated in the boundary layer. It's the main, almost the only momentum sink for the rest of the atmosphere. It's the primary sink of aerosol and water. It's the only source, of aerosols and water, except if you think of what escaped and then got affected, but basically this is where aerosols and water come from, and it's a very large source of heat. It's not the only one. There's other sources of heat, for example, interception of radiation by clouds, but it's a big source of heat. So all of these kind of fluxes between the atmospheric boundary layer and the free troposphere are extremely important to get right in coarse models to get the large scale dynamics right. So you're focusing on this atmospheric boundary layer, and we define it as the region of the atmosphere that responds to Earth's forcings within an hour. So if that is the case, that means that the diurnal cycle is extremely pronounced in the atmospheric boundary layer. And what that means is during the day, the surface is hotter than the air, so you get basically hot air at the surface that rises because of buoyancy, and you get very strong mixing. This is the unstable or convective or mixed boundary layer, which has a lot of very strong turbulence. So just for you, if you don't know, so just by having a flow over a surface, you're going to get friction, and this friction with the surface is going to produce turbulence. This is what we call shear or mechanical production of TKE, which is turbulent kinetic energy. Now, when you add the buoyancy, when you add the heat effect to it, during the daytime, the buoyancy adds even more turbulence by basically heating the air close to the surface and basically causing convection, like Rayleigh-Benard convection. Now, during the night, something else happens. During the night, the Earth's surface cools by radiation, so you get colder air close to the surface. Now, that makes air close to the surface colder and more dense, so it's actually more difficult to mix. And if you try to mix it, you'll actually be destroying some TKE that was produced by the friction and converting it into potential energy. So basically, during night, buoyancy destroys turbulence, and during the day, it adds to turbulence. So this is a much weaker, is a boundary layer with a much weaker turbulence, and it occurs during the night, but it also occurs very importantly in polar region where you have ice and snow at the surface and very little radiation, so the surface is very often colder than the atmosphere. Now, if you want to represent these dynamics, so this or that or anything, basically any kind of turbulence in the ABL, these turbulent eddies are too small. They're about 1 kilometer, so you are not able to resolve them in weather and climate models. So what you want to do is parameterize them, okay? And the way you would do it in the simplest model possible that you can think of, you would say that the fluxes between the Earth and the atmosphere are given by some basically this type of kind of transfer models or flux profile relations or whatever you want to call them. We're basically saying that the surface stress tau is related to the square velocity, and one of the parameters that enter here is the transfer coefficient for momentum c. And the same thing for heat, we have a heat transfer coefficient and a humidity transfer coefficient. If your first grid point is in the atmospheric surface layer, if you believe Monod book of similarity, you could use it to give you Cm and Ch and Cq. So if you write the Monod book of flux profile relationships, you can find a direct correspondence between Cm and the parameters of Monod Bukov, including ZO and Z over L, which is about the Flux-Richardson number. Now, if you're away from the surface, or if your first grid point is not in the atmospheric surface layer, or if you basically are in conditions where one in Nabokov breaks down, you have something quite similar. So instead of basically C, we have a K, and now we multiply it by a gradient. So this is the momentum diffusivity and the heat and moisture diffusivity that are caused by turbulence. So these are turbulent diffusivities, right? And you basically want to write these models for the turbulent flux of momentum, of heat, and of water vapor. One way of basically kind of modeling these diffusivities is to say it's a length scale multiplied by a velocity scale and modulated, increased or decreased depending on the stability, which here is given by a gradient or a bulk Richardson number, and S is the mean shear in the atmosphere. So these are kind of, probably you're familiar with some versions of these equations. And so this is basically how first order models do it. Higher order models do it somewhat differently, but can, again, you're basically trying to get a TKE, you're solving a TKE equation in the 1.5 model to get a K or something along these lines. And of course, you need to know something about entrainment processes if you want to complete the problem. Now, if we focus below the entrainment, one of the problems with this formulation of Km is some function of shear and the mixing length and some function of the Richardson number. So this is the typical model we use here. We need to basically make it a function of the Richardson number, and so most of the, what we call sharp tail models, tell you that above a certain stability, buoyancy destroys all the turbulence and you have nothing left, so basically your Fm is 0 or very close to 0 and you don't have any turbulent fluxes. And this basically is based on the linearized perturbation analysis that say that somewhere in the region of 0.25 to 1, if in stable flows, turbulence is completely dissipated depending on if you're 25 if you're going turbulent to laminar, turbulent to laminar 1 if you're going in the other way. But basically these tell you that there will be very little turbulence in these conditions. The problem is invariably if you do observations, you will find that basically there's turbulence at much higher Reynolds number. And some questions come up. Is it a failure of the linear analysis? Is it turbulence that's kind of propagating from breaking waves or Kelvin-Helmholtz instabilities that rather than being produced locally? Is it because our bulk Richardson number is large, but locally we have regions where it's small, and so in these regions we get turbulence production? Is it effect of surface heterogeneity? So is it, again, kind of the unresolved heterogeneity of the domain? Is it mesoscale variability effect, etc., etc.? Coarse models try to fix this problem by trying to get a larger critical Richardson number, and we call them long-tail models because Fm decreases much more slowly with Richardson number. A more serious problem is illustrated in this data set that's basically was collected in Barrow, Alaska, and I'm analyzing it with some collaborators from Penn State. Here, basically, turbulence is so weak that it's intermittent. So you get burst of turbulence and then no turbulence. And normally, this model will tell you, or this model will tell you, if there's more turbulence, K is higher, and basically the fluxes are higher. And so, or in another way, if you have higher gradients, you get higher fluxes. This is what an eddy diffusivity model tells you. This data set shows the opposite. Higher gradients give you lower fluxes, and lower gradient give you higher fluxes under intermittent cases. So in this period, we have an H of almost 0, but very high gradients. And in these periods, we have gradients of much lower gradients giving you much, basically, higher fluxes. And the problem with intermittency is that the eddy diffusion hypothesis just breaks down. You have no turbulence, and that basically increases gradients and shear. So gradients increase, but there's no turbulence, so there's no flux. And then suddenly there's a turbulence burst. This turbulent burst produces fluxes and reduces the gradient. So in intermittent cases, eddy diffusion just doesn't work. So okay, so to give you a synopsis, basically what the problem is that we have a long way to go before we really understand turbulence in the ABL. Monin, Obukov, and eddy diffusivity don't cover nearly all the cases that we need to know. And particularly, I'm interested in the complexities arising from stabilizing buoyancy effects or surface heterogeneity and complexity. We also have a long way to go, even if we understand this, but we don't. Even if we understand it, we then have to kind of parameterize it effectively in weather and climate models. And that does make a difference. Marat was just giving me an example today about how that can basically alter your time of precipitation. But this is a simulation from WRF, where we compare WRF to observations. And you see that most of the time during the peak, this is temperature, and this is in the BWI airport close to Baltimore. During the peak temperatures during the day, the errors are acceptable. You see much larger errors at night, and this is if you run WRF or other models, you'll always see much larger biases at night because we don't understand stable boundary layers as much as we do convective boundary layers. And so it's a problem that can be significant. This is 3 degrees difference in temperature. My colleagues at GFDL tell me their models have up to 10 degrees or so biases in polar regions, again under these stable conditions. But we shouldn't lose hope. There is hope. There are new simulation approaches with higher computational power that allow higher resolution, that allow us to basically advance the field a little bit, well, more than a little bit. There's a wider availability of better field observations that are also very helpful. So that basically eventually can give us better grounding to test new theories or develop new theories, and then eventually use them for better models, modeling at the large scale. So before I proceed, I'm going to give you a 2-minute introduction to turbulence. So any turbulent flow, including the one in the atmosphere, basically you can think of large and small eddies. The large eddies are specific to each flow. They're contained in the energy production range. The intermediate eddies are what we call the inertial range. They're not interacting with the surface, most of them. So basically, they are not very sensitive to the surface. And the smallest ones are the dissipation range, where the turbulent kinetic energy is being dissipated. This is where it is being produced. And these are, again, very universal. They're not very dependent on the flow specifics. So in weather and climate models, if you have 5 mesoscale models, you can resolve some of the large scales. Now, you might not want to resolve them because you could be double counting turbulent fluxes. I'm not going to go there. But the basic idea is either you're resolving only the very large scale, or even better, you're not resolving anything, and you're modeling the effect of all the scales of turbulence. So you're modeling the fluxes that is being produced by everything from the smallest to the largest scale. This is what any weather or climate model should be doing. If you want to resolve all the scales, you will be doing direct numerical simulation. So you need a grid scale, which is slightly larger than the smallest scales here. And basically, you would be doing direct numerical simulation and resolving everything. Obviously, you run into problems where your whole box has to be very small, because basically you just don't have enough computing power. An intermediate approach is to do large eddy simulation. In large eddy simulation, instead of basically saying I need to resolve the smallest thing, you basically think of the box you need, and then you resolve as much as possible, as much as you can computationally afford, right? So then, ideally, your delta will be in the inertial range. It doesn't always tend to be the case. But ideally, your grid scale will be in the inertial range, and you can resolve basically all of the energy production range and part of the inertial subrange. So the idea of LES is, if you're interested in the fluxes, the large scales that you can resolve are the ones that are carrying most of the fluxes, so you don't need to resolve the very, very small scales. And the small scales which you need to model in LES are more universal, so they're easier to model than, let's say, all the scales of turbulence that we need to model in mesoscale models. So a typical model for that, which is also an eddy diffusion-based model, is the Smagorinsky model, which basically says that there's some subgrid scale diffusion multiplied by a strain, the strain rate tensor here. And basically, this is the expression for it. We have a coefficient here. I'm not going to dwell on that, but in our code, the results that I'll show you are with a scale-dependent dynamic model, where we try to look at the smallest resolved scales between the grid scale delta and 2 delta, and between the grid scale delta and 4 delta. So these are the smallest resolved scales, which should look like the unresolved scales. And we try to learn about, from these scales, how we would model these scales. So we try to get the model constant dynamically from these. To do this, a dynamic model, typically you have to average over some homogeneous directions. If the flow is complex, you cannot average over horizontal planes because they're not homogeneous if you have a building. So what we implement is we average the error over fluid path lines. So I don't want to dwell about that. Just to a quick overview, the way we develop these subgrid scale models for LES, or the way we test them, one approach is the so-called a priori approach, which is basically you take DNS or measurements, you artificially filter them into resolved, LES resolved and exact subgrid scales. And then you see how a given model would basically use these resolved scales to produce modeled subgrid scales. And now you can compare the exact and modeled subgrid scales, and you can see if you can improve or throw the model away and bring a new one. So the code I'm running with, we've done a lot of validation for it. This is to show that it produces the log low, it's in red. It produces the log low better than the standard Smagorinsky or a scale invariant model. It produces also the -1 spectra slope in the production range and the -5/3 in the inertial range, etc., etc. We've also kind of validated it for other flows. I don't want to go into details. So we take this picture and basically now think about how, instead of DNS and LES or observations in LES, let's think about what we would need to do to improve mesoscale or climate models. In this case, you can have LES or measurements that are going from all the scales to a meter. Now again, in these models, we need to model the effect of all of turbulence. So now you have everything. You can split it artificially into the mean and the turbulence. And then you can see how your closures, these kind of Eddy diffusivities, how a given model can take the means and give you model turbulence. And then you can see if that model works or doesn't by comparing it to LES. So this is again an a priori approach of testing it. The a posteriori would be just to implement this one in a mesoscale model and how to see how the mesoscale model performs. So we've done some LES and we've used them to kind of test a priori and a posteriori new parameterization for stable boundary layer in the single column model of GFDL. A single column model, I'm sure you all know it. It's basically, we have the Coriolis term, we have the geostrophic forcing, which is the pressure, we have the unsteady or tendency term, and we have the turbulent fluxes. And this is the U, V, momentum, and theta equation. The model is one-dimensional, horizontally homogeneous, dry boundary layer. We don't have subsidence. We're driven by the pressure gradient given as a geostrophic wind. And the problem, this problem illustrates the closure problem. We have 6 variables, U, V, theta, and U, W, V, W, and W, theta, because these are kind of higher order moments, so we don't have them, but we only have 3 equations. So the reason we need these models for this and this and this as kind of Eddy diffusivity, we model this as basically a function of the gradient of theta, is that with these extra models, we now have 6 equations and we close the system. So again, the simplest way to close them, I'm coming back to it, is this basically Eddy diffusion, where we say that the fluxes are proportional to the gradients with some Eddy diffusivity here. And you need a Prandtl number, which is the ratio of the momentum to heat diffusivity. The gradient diffusion hypothesis, if you want to test it, you first have to test its assumption. So it assumes that the flux and turbulence are produced by local gradients and conditions, which is not the case in a convective boundary layer, but in a stable boundary layer, it might work. It assumes that the fluxes and gradients are aligned in a simple Ekman boundary layer. That means that with the turning, basically you don't have a parcel with a strong U momentum being transported to a high elevation where the U momentum should not be that large. So basically it says that the fluxes and the grade, if you think of them as basically vectors or tensors, they should be aligned. In 3D, they are basically, for momentum, they are tensors, for heat, they are vectors. Again, we saw, so if these assumptions are satisfied, then a model of this sort, which is basically is relying on this Eddy diffusion hypothesis, should work. So if that should work, the question become again. So if that should work, the question becomes, what are the values of the case? So what are the diffusivities? What is the value of my mixing length? How does it depend on Richardson number, etc., etc.? So I'm going to see if the gradient diffusion works. So we're going to test these assumptions, and then if it works, we're going to try to find what these values should be. We started with a famous test called the Gable-Swan test. These are basically the parameters given to it. For the sake of time, I'm not going to go through it in detail. I'm just going to tell you that we have basically 160 cube simulation, and that we ran for 10 hours, and we only look at statistics from the last 3 hours. So the Gable test was studied by multiple LES by Barrett al. And it's a weakly stable case. This is important, weakly stable case. And this is the surface stress, surface heat flux, and boundary layer height that they got. And you see that our LES basically fits within the range of the different LES that they have. Also, you see that if you change the resolution of our LES, all the results kind of converge for the higher resolution, and they all are within the basically range of Barrett al. If you also look at gradient or profiles of wind velocity, surface stress, heat flux, or theta, again we are within the range of Barrett al. But this is a weakly stable case. But it shows us that basically our LES is robust enough to study the dynamics of stable boundary layers. So the LES is not in question here. LES is the truth, and it's the single column model that's in question. So instead of just doing case A, which is basically the case I was just showing you from Gable's, we basically wanted to see what happens when we increase stability. So we went to much faster cooling rates of the surface. That's going to give you more stable conditions. And with that, you get a decrease in the boundary layer height. You get a decrease in the friction at the surface. And you get a decrease in the Monod-Book length scale, etc., as you would expect. We also, these are all kind of steady state simulations. We also wanted to see what happens if you change the surface flux cooling rate. So what if you have a cloud layer that comes above your surface, and suddenly you basically have a much weaker cooling rate, or if it goes away and you have a much faster cooling rate. So we did two simulations, a hat and a step, where the cooling rate changes by an order of magnitude, either suddenly or over the course of basically 10 hours, which is kind of what the night conditions last. So what you observe is, again, if you do these simulations with LES, as you increase the stability, the basically supergeostrophic maximum decreases in height but increases in magnitude. The temperature gradients are higher, are larger. The velocity gradients close to the surface are also larger. The heat flux at the surface increases because the surface is cooling faster, but the momentum transfer to the surface, or the momentum flux at the surface stress decreases. This is going to be important towards the end. So with increasing stability, we see stronger wind shear, stronger T gradients, larger heat fluxes, but smaller momentum fluxes. In general, higher stabilities give you weaker coupling, and in the limit, we observe Z-less stratification. And the idea of Z-less stratification is that if the coupling is so weak, at some point, what happens at 500 meters or 400 meters is completely independent of the distance to the surface, because the surface is not affecting these dynamics at all. As another validation for the higher stabilities, we try to see if in our LES we partition the destruction of TKE correctly, and the sources of destruction are either by viscous dissipation or by buoyancy destruction in the resolved scale, or by buoyancy destruction in the Subgrid scales. So we compare our LES, which is basically the dots here, to field observations that we've done over a glacier, which is given by the lines with the variability bars. And you see, actually, this was quite encouraging. This was quite encouraging. So these are the more stable cases, and you see that the partitioning of the destruction of TKE is reproduced by the LES, matches the observations So this was quite encouraging. There's a little bit here under basically estimation of the result, but for the higher stability cases, the destruction. So this is kind of another validation that we've done. And so so the first test that we've wanted to do is whether the stress and strain are aligned. So remember, the alignment is basically is an assumption of the Eddy diffusion hypothesis. So in convective boundary layer, this angle between the two will be large, up to minus 30 degrees or plus 30 degrees. We see that in the stable cases, and the further you stabilize it, the more these two are aligned. So stability reduces the vertical extent of the eddies and makes this basically alignment assumption even better. So this assumption is well validated under stable conditions, so that's good. Now, if that is the case, we wanted to see if we take these diffusivities, these cases from the LES, we compute them from the LES, and we impose them in the single column model, do you get the profiles that are exactly similar to what you have in the LES? So does this Eddy diffusion model, can it represent all the nonlinear processes or nonlinear transport and action of turbulence? So the LES is in gray. The single column model results with the diffusivities K imposed from the LES is in black. And you see that it actually does pretty well. You almost don't see any difference in the heat fluxes, very little difference in the momentum fluxes. Again, this is for a weakly stable A case and strongly stable F case. Some minor differences, less than 1 degree or about 1 degree in temperature, and overall some discrepancy, but again, it's quite, I would say it's quite acceptable for wind speed. So basically, the stresses are aligned with the strains, and if you know the Eddy diffusivity, you can basically reproduce what LES produces. So the problem is not the Eddy diffusion hypothesis itself. The problem could be how we estimate the Eddy diffusivities. So then we went back to running the single column model with the models of the diffusivities rather than the values from LES. We used the long tail model of GFDL and a sharp tail model. And for weak stabilities, everything works fine. For stronger stabilities, things start looking pretty bad, actually, for these cases. We tried tuning the parameters for these. It didn't improve these very well. And you even see bigger problem with the stresses and the fluxes, certainly for the stresses. You see that basically there's both the dot dash and the dashed line, which are these two models, deviate quite significantly from, for the stronger stability cases, from the LES. The problem, what we observed, is that if you use this formulation, you're basically saying I have some diffusivity under neutral condition, which is this part, and which basically you kind of, the ln, you write it that way. And then I'm reducing it by multiplying it by some function of the Richardson number. If you look at this one, it has some dependence on Z. And if you multiply it by some stability function, the dependence on Z is unaltered. So basically, you don't get any Z independence, or at least if you do, the Z-less or the independence or dependence on Z does not change with stability, but it should. The Z dependence should be strong when it's neutral and absent when it's highly stable. But again, this one, we have a function of Z that we just multiply by a function that is not a function of Z. So the dependence on Z is not altered by this version of the model. So we tried a very simple fix. Is instead of multiplying it by a function of the Richardson number, we said, well, if the Richardson number is very small, it will impose its own mixing length scale. And so we formulate a mixing length scale like this, so we don't have any multiplicative parameter here. But this one directly now depends on the Richardson number in this way. And so you can imagine if the Richardson number is very large, this term will dominate, and the Z term will become unimportant, and this L infinity, which is mixing away from the surface, will become unimportant, and we get a Z-less model. If we are close to the surface under close to neutral condition, these terms are weak and this term dominates, etc., etc. So the asymptotic behavior of this model is better. this is what I'm showing you here. I call it HBG, one Bou-Zeid and Golas model. And this is the light gray one. You see that for the weakly stable condition, it performs the same. But for the strongly stable condition, now it performs much better than the other models. And its performance is comparable between weak and strong stabilities, which the two other models, they don't have. And we tried tuning these models, it just doesn't work. Also, if you see how the surface flux changes with stability, so these are the smaller surface fluxes, so these are the more stable cases. Under neutral or weakly stable conditions, all the models are fine. As you go to higher stabilities, our model still is able to capture the surface flux as produced by the LES, while the other model diverges significantly. So again, a very simple fix, still a first order model, but with a better asymptotic behavior, and we get much better results. Now, the transient cases are more tricky. This was all steady state. The transient cases are more tricky. You see basically that, again, this is the hat and the step. We have problems matching the exact initial conditions, but even if you look at the last period, certainly our model produces better results than the two other models. The solid gray line is much better, actually. But we still have discrepancy and basically larger error in the transient cases. So does that mean the problem is solved? I mean, does this kind of simple tweaking of the mixing length doesn't solve the problem? Not at all. Obviously, transient cases are much more challenging. There are other aspects that I didn't talk about here. And the reason is none of the closure take into account the fact that turbulence has memory. So if you suddenly transition to stable conditions, turbulence is not going to suddenly equilibrate and go away. So if you have unsteady conditions, there's this memory effect that can become important. There's a whole suite of other problems. We assume scale separation, but under nighttime conditions, we don't have scale separation. We have small scale forcing variability that affects the atmospheric boundary layer. Surface heterogeneity, intermittency, which I talked about at the beginning. So we're far from solving all our problem, but at least now we basically have tools that allow us, like high resolution LES with good subgrid scale model, that allow us to try to improve our understanding. I'm going to go quickly through a couple of problems and give you just a flavor of what we're doing. This is the problem with the geostrophic wind. Just assume that, so we know that there are small, what Larry might call sub-mesomotions that at nighttime kind of want to meander and change the direction of the wind. Again, this is not accounted for in any of the closures. So all of these similarity theory assume stationary conditions, but meandering motion and other mesoscale variability can cause this to break. Forcing variability it will induce nonlinear effects on TKE and its budget in the APL. This is a beautiful art piece by my colleague at Penn State, Marcello Ciamecchi, who basically, this is a problem that happens in the spring in polar region where you start having bleeds and polynias that form, and you have very striking variability from cold ice to hotter water. And the difference in temperature is significant enough that basically you have small-scale transition from stable to unstable conditions, etc., etc. So a student working with me, Stimit did some LES of this case, and okay, so you assume that basically advection will have an effect, but that you still get more turbulence over the stable case, or over the unstable than the stable case. In fact, we find that advection is so dominant. This is a periodic simulation, so you have hot patch, cold patch, hot patch, cold patch. You see that when you enter the hot patch, the cold patch had destroyed all the turbulence. It takes a little bit of time for turbulence to be generated by buoyancy, so turbulence starts growing. But by the end of the hot patch, even though it's 3 kilometers, you don't have much turbulence. When it enters here, actually the conditions in the atmosphere are still favoring turbulence production. So it kind of continues growing, and then at some point it starts being destroyed until this point. So eventually what we find is more turbulence over the stable patch, which basically would increase fluxes from this patch significantly and reduce fluxes from this patch. So again, a very unexpected and nonlinear behavior. Again, if you look at the structural differences between turbulence between a neutral a stable and an unstable boundary layer, you find sharp differences. And one question is, can you link this kind of topological view of turbulence to the statistical one? Can you use this understanding to help you develop better turbulence model? We're also doing some DNS. Again, this is kind of DNS with increasing Richardson number. You see that for the lower Richardson number here, you basically get kind of a steady state situation after a while, after you forget your initial conditions. When you start increasing your Richardson number, you start finding these kind of intermittency behavior. In fact, in this graph, which is the angle between the geostrophic wind and the surface wind, if you have laminarization or constant eddy diffusivity, you get 45 degrees. This is the classic aqueous solution. You see that for the highest simulations, we're getting 45 degrees, so we're getting a complete damping of turbulence and reverting back to kind of molecular viscosity. And then you suddenly get a burst, which makes it more turbulence, and then it dies down again. So this intermittency that I showed you at the beginning, you can see it. This is the volume integrated TKE that's also kind of oscillating for the higher one. This is, again, a very interesting study. So we were doing this DNS, and we wanted to see how buoyancy destroys TKE and how that generates lower TKE under stable conditions. What we find was very surprising. We find that under a lot of conditions, direct buoyant destruction of TKE is extremely small. It's not important. What happens instead is that, and these are the budget terms, you see that the buoyancy is now, we put it in the residual and it's almost zero. For some other cases, slightly larger. But the big thing is the production of TKE by shear has dropped significantly, and we were kind of surprised. But what we observed is that the main reason that TKE is lower in stable ABL is not because of direct buoyant destruction, but rather because the friction at the surface, U star, decreases, as I showed you at the beginning, because of weaker transport of momentum towards the surface from aloft. So if that is the case, you have weaker transport of momentum, weaker shear, and this weaker shear reduces the shear production of turbulence. So it's really a damping of the production rather than a destruction that explains a lot of the reduction in TKE under stable conditions. To summarize, so LES can be used to test and improve ABL parameterization in various coarser models. Eddy viscosity closure are not the problem. They can reproduce the profile in a homogeneous steady ABL given the right diffusivities. Their basic assumptions are right, at least under steady state conditions. But the formulations to get these cases are basically not good. What we have now is not good. We proposed a new formulation that was still very simple and was able basically to improve the performance of GFDL single column model a lot. But we still had some problems under transient conditions. Again, the problem of the ABL is far from being resolved. We didn't look at heterogeneity in these kind of single column model runs that I showed you. So what I showed you at the end tells you that heterogeneity is extremely relevant. And atmospheric chemists are very interested in this because you have this bloom in chemical activity in the polar region. And a lot of it depends on the fluxes of halogens from the surface and fluxes of other chemicals from the surface. And so the fluxes at the surface, if you have transitions, could be drastically different. Unsteadiness and mesoscale variability is another problem, again, that still needs more work. And again, there's a fundamental problem of understanding how turbulent flows are affected by buoyancy. What's the action of buoyancy? How does it really act? Can we kind of try to understand the structure or form of the eddies and relate it to the statistical description of turbulence? So there's a lot more work to be done, but at least now we have basically the tools, and there's multiple groups. We're not the only one to work on that. This is a cool picture from an experiment where, of course, this data is not usable, where the sonic anemometer was completely frozen here. And I want to thank my basically funders, and if you have any questions, I'm all ears.
Yeah, so in your formulation of the Eddy diffusivity,
you just use the length scale multiplied by the here, you no longer use the f function. Is that what I?
Yeah. So we don't have a function of the of Ri. So this formulation is trying to reduce the mixing length as a function of the Richardson number.
Okay.
Instead of multiplying this neutral mixing length by a Richardson function of the Richardson number, we add a term with the Richardson number instead of being a multiplicative one. And when you add it, the asymptotic behavior is better, we find, under highly stable conditions because it becomes Z-less.
So it's like a different formulation of the Fi, basically. If
yes,
you do a Taylor expansion, it's
yeah,
similar.
yes.
Right.
So yeah, I guess if you do that, you can still find a multiplicative form.
May not cover the whole range.
Yeah, though you might not be, you might need a couple of terms in the Taylor expansion, which will make it kind of have an extra term here.
Now then, the second question about the stable boundary layer regarding the TKE production and dissipation. So that does not change in the parameter. That effect is in the current parameterization. Is that right?
So the Richardson number is the ratio of shear production or destruction divided by TKE production by, buoyancy production or destruction divided by shear production. Now, so what our results show is that it's not only the numerator that changes, but also the denominator. So it's not like the denominator is constant regardless of stability and then you destroy or produce, but the denominator itself changes. Now, what that tells you is that you can have basically, if the denominator is not constant, what that tells you is that you can have the same Richardson number, right, but with very different levels of TKE. Because, if you reduce the numerator and denominator or increase the denominator and denominator, you could get the same ratio, but with different levels of TKE. So what that could tell us, but we're not there yet in our analysis, is that basically the Richardson number might not be the best stability parameter because it is based on so the Richardson number could work because it has the TKE production which is reduced in the denominator. But that could give you some problems, but we're still kind of looking if that really gives you problems or it doesn't.
Yeah, but the budget itself does not tell you, say, which effect is considered because both the denominator and the numerator are going to be calculated based on the turbulent closure. If you integrate the model, the shear would change with turbulence, the vertical gradient of the temperature.
Yeah.
Change,
So
right?
so if you if you were doing kind of higher order models where you compute these, yes, certainly.
Yeah, also there's this mentioned high order models. Your results suggest very good kind of that this simple gradient kind of model works very well. So what's your comment? Do we really need then high order closure models?
So higher order closure models are theoretically better. If you're higher order, if you're doing second order closure, you're closing for the third. Yeah. I mean, the problem with higher order closures is that people think it's the magic bullet, that if you use higher order closure, it's gonna work. Well, no. If it only works if you do a very good job with your higher order equations. If you start making a lot of assumptions in your higher order equation and bad closures, then your higher order term that you think that you want to put in your first order equation could be worse. I mean, so to go to higher orders, you really should do a good job at all orders. And if you do that, theoretically you get, so what we did is we tried to play with a 1.5 order of closure where the TKE equation is reduced to, is kind of equilibrium. So production equal dissipation and buoyancy with even a tendency term. That was not enough, so that did not give good results so then we dropped it and just looked at it, didn't add it, yeah.
So I didn't understand why the shear production tends to drop after stability.
So this is basically, so shear production is basically, so shear production is a strong function of U star, right? It's basically, I mean, it goes like U star Q. And when you go from mildly stable to strongly stable, turbulence activity in the atmospheric boundary layer decreases. So you have less momentum transport to the surface. So you have a drop in the shear. And if you have a drop in the shear, that basically results in a drop in, and we looked at the budget of fluxes and other things to show that. I didn't go through the results. But it turns out that it's really kind of the drop in the transfer of momentum that causes this drop, which then reduces production.
So at the beginning, and you mentioned later, regarding this opposite relationship of the flux with the vertical gradient.
Yeah.
So you still do not have a solution for that, is that right?
We're working on one, but that's a difficult one because, I mean, this is really kind of the frontier of things where basically you, well, the good news is we were not sure we would produce this intermittency in DNS, and we were able to produce it, so that's good. So in these cases, what we find is that initial finding is that instead of kind of using a diffusivity, well, in stable boundary layers, instead of trying to use TKE to model diffusivity, a much better parameter is just the variance of vertical velocity, because this is what transporting things. So we find actually that the fluxes are related enough to the flux of vertical the variance of vertical velocity. And so instead of a TKE or a 1.5 order closure based on TKE or an Eddy diffusivity, maybe you can just solve the equation of the variance of W. And that becomes a good, gives you a good estimate of the diffusivity that would basically drop and increase with these fluxes. But it's a complicated problem, so we're kind of analyzing the data.
So you think the first order model should still work? You can just change it?
No, we would, yeah. Well, okay. So the first order would work. You can always put a K, but this K would be dependent on W prime squared, the variance of W, and it would be dependent in a way that would basically give you these strengths. So it will be sharply reduced when these are large and based, but we don't know if so here we kind of measured the variance of the vertical velocity. If we try to model it, we don't know if we're successful. And notice that these, this is like 20 minutes, right? So if you average over a super long time, maybe kind of Eddy diffusion would work. But now, the scale of the intermittency is so large that even if you average over 30 minutes, you still get basically very weak fluxes with very strong gradients. So the time of intermittency is very large.
Well, if there are no more questions, let's take this one again.
Happy to meet you. Hi. Thank you very much. Thanks. So what do you work on with process things?
Climate model.
Okay.
I work with Chris Mola.
Okay, yeah. I'm trying to understand how to put this in the GFDL model. I mean, they're so busy with the ITCC things, they spend most of their time doing the ITC. But I have a student now actually they hired to do some other work, who was working with me, who might have some time to implement these in the